we're going to look at the idea of being able to tie in everything that we did with respect to left endpoint, right endpoint geometry, and then being able to work in something called the fundamental theorem of calculus. Okay. Now, the fundamental theorem of calculus helps us to get a precise value for a definite integral, right? And realistically, all we're going to do is to evaluate a definite integral by using fundamental theorem of calculus is we're going to find the antiderivative. We're going to substitute the upper bound, substitute the lower bound, and subtract. Okay, so that's what the fundamental theorem of calculus says. And so what we're going to find is that in a lot of cases, it's much easier to use the fundamental theorem of calculus than it is to be able to use the right-hand endpoint, the left-hand endpoint, and then also geometry, okay, to be able to evaluate. Now, let's take a look at a really basic example to kind of tie all this together. So we have a definite integral, 2x plus 1 from 0 to 1. We're going to sketch the graph that's represented by the integral. We're going to use the right-hand endpoint and the left-hand endpoint to approximate the integral. Then we're going to use geometry. And then finally, we're going to use the fundamental theorem of calculus to evaluate the integral. Now, these two should be the same, because remember, geometry and fundamental theorem of calculus are going to give us precise values, all right? It should be estimated reasonably by parts B and C, okay? But let's figure out let's try to go forth and see what happens with this. Okay, so letter A, really easy, right? We know it's a linear function from 0 to 1, right? So if I were to graph this, I know if I substitute 0 back in for x, that's going to give us a 1. And then if I substitute 1 back in for x, that gives me a 3. All right, so, and I know this isn't the scale. And it does say for us to sketch the area represented. So this would be the area that's represented by the curve. All right. Now, we're going to have to use the right endpoint to be able to approximate this. So we're going to need delta x, which is going to be b minus a over n, or 1 minus 0 over 4, which is going to give us a quarter. That's how much we move, and that's also how much the base of each of our rectangles is, okay? So for part B, when we're using the right-hand rule, okay? So here's our graph, again, exaggerated, and we're going to be using the right-hand rule, right? So this is a right hand right here, and that's one of our rectangles. And then we have another one, and again, just imagine that these are all the same size. And then I'm not horrible at drawing. All right, this is going to be 0, a quarter, a half, 3/4, and 1. Okay, and again, all I'm doing is I'm just adding a quarter each time. We know that the base of each of these rectangles is a quarter, right? So for us to be able to approximate the value using the right endpoint, okay, and remember, right is going to be an overestimate. This is going to be a quarter times all the function evaluated at these 4 values, okay? So it's going to be 2 times a quarter plus 1. All right, so we go back up here. So 2 times a quarter plus 1, and then 2 times a half plus 1. Okay, so this will be 2 times a quarter plus 1, and then 2 times a half plus 1, and then 2 times 3/4 plus 1, and then finally 2 times 1 plus 1. All right. Now, if we compute all that out, okay, all these ones become a 4. All right, so, and I'm just doing this quickly, so as to not use technology. All right, so we have a 4 there, and then this is going to be 2/4, and then this is another 1. So we have a 1 here. So this is going to be 2/4, and then this is going to be 6/4. So 2/4 and 6/4 is going to give us 8/4, which is a 2. We have a 1 from there, and then we have a 2 from right here. All right. So if I add all of these up, I get 4 plus 5, which is 9/4, I believe. If I did all that computation correctly. It might be best just to go ahead and use Excel really quickly, all right, just to make sure we have it correct. So we have 1/4, and we had 2 1/2, And then we had 3/4, and we had 1 for our right endpoints. This was 2 times a1 plus 1. All right. And this is going to be the sum, which was 9. And so if we divide that by 4, that is 9/4. Okay. So we did get it right, just making sure. All right. Now we're going to use the left endpoint. All right. And remember, the left endpoint is the same thing, except we're going to get rid of this 2 times 1 plus 1, and we're going to replace it with 0. Okay. So that's going to be the same thing, except we're replacing 1 with 0. Right. So that's going to be 1/4 of f at 0 plus f at 1/4 plus f at 1/2 plus f at 3/4. All right. And so if I just wanted to, I could go back here. I could replace this 1 with a 0. That should just give us 1 anyway. The total is 7, and then we divide that by 4. All right. So this should end up being 7/4. All right. So we have 9/4 and 7/4 that our area should be between. All right. So the area should be between 7/4 and 9/4. Boy, I bet you 2 is a good number. All right. But let's see if it is 2. Now we're going to use geometry. All right. So we go back up here, and we could just draw a line, and we can get a rectangle, and we can get a triangle out of this. Okay. So this is going, remember, this has a base of 1 and a height of 1. This has a height of 2 and a base of 1. So if I call this A2 and A1, so we know that area 1 is going to be 1 times 1, which is 1. And then area 2 is going to be 1/2 of 2 times 1, which is 1 as well. And so the total area is going to be equal to 2. All right, now that's the precise area, which makes sense because certainly 2 is between 7/4 and 9/4. Now, that's all stuff that we knew how to do from the previous section. Let's use our fundamental theorem of calculus. And actually, this is going to make it really easy for us. Okay, so fundamental theorem of calculus says that we have to evaluate the integral from 0 to 1 of 2x plus 1 dx. Now, what we're going to do is we're going to find the antiderivative of each of the terms. So this is going to be 2x squared over 2. So remember, you add 1, divide by the new exponent. And then anytime you have a constant, you just multiply by x. All right. Now, we're not going to use plus c because this is a definite integral. Instead, what we're going to do is we're going to keep those limits of integration as 0 to 1. Fundamental theorem of calculus says we're going to substitute the upper bound in and to subtract out the lower bound. This is going to simplify into x squared plus x from 0 to 1. If I substitute 1 back in, I get 1 squared plus 1. So that's f at b. F at a is going to be 0 squared plus 0. Right? Now, clearly, that just goes away. 1 squared plus 1 is going to be 2. All right, and that jives really well with what we got from before. All right, so this is a little bit easier than having to draw out the geometry of it and then being able to construct it. But moreover, there's a lot of functions where geometry just can't be used because we can't get nice geometric shapes to be able to find the exact area using that geometry. So this is our fundamental theorem of calculus, which works really nicely. Now, we're going to go through a bunch more of these types of problems and illustrate how to find the area bound by the curve if it's not necessarily a really nice function. Okay, but this is kind of tying everything that we've done so far in with the fundamental theorem of calculus.